Hey everyone, today's lesson we're talking about evolution, and really we're talking about people's theories on evolution over the years. I say evolution of an idea, but really what I'm talking about is changing ideas that all contributed to our current theory of evolution. So, as mentioned in lesson one, evolution is only a theory. Okay, some people may agree or disagree with that. We have a ton of evidence to support the theory of evolution. Today in 2020, we support evolution by what's called natural selection, and we'll spend quite a bit of time in this unit talking about that. It is a shorter unit, so you will have noticed that we're going to have a quest for this unit, which is just a mini version of a test. So there's not a whole lot of information on it, but one of the big ones is all of the scientists who went into proposing different theories of evolution over the years. So in the notes here, what I'm talking about is really early ideas of origins of the living things. And for a long time, there was a belief that all living things were created in their present forms and they were immutable, which means that they have never changed over the years and they cannot change in the future. This understanding was based surrounding religious teachings. And then I mentioned a few familiar names, hopefully familiar to you, that started to come up with ideas about organizing organisms and sort of seeing that they were different from one another. So, as an example, Aristotle believed there was some type of hierarchy. So, things are very simple, and then we see things are very complex. Carl Linnaeus, who we spent some time in Unit 1 talking about, thought of the idea that life has changed over time. Okay. And Erasmus Darwin, who is Charles Darwin's grandfather, suggests that all life may have come from a single original source. And so we were talking in Unit 1 about the protists as theoretically the very first eukaryotes. So what we're talking about there is a theory behind how life came to be, which is a term that we call abiogenesis. So that just means the theory of how life developed from non-life, essentially. So a little bit more about that afterward. In here, I just want to mention quickly, we're not super concerned about the dates. So you will see that beside each person's name, I often will put a date. That is when that person lived. And it's just to give you a bit of a scale as to sort of like moving forward in time, how these evolutionary ideas have changed. But you won't be asked, for example, to put them in any sort of order or to replicate those dates in any way. It's more just to understand that our ideas have gone from pretty basic when we didn't have technology as much into something that's really become a lot more detailed. Okay, as with everything else, we learn more information and so we continue to change the theories. So the first person that I'll tell you about, his name is Buffon. He noticed that there was a connection between physical structures and their functions. So some organisms have what seem like useless features, but these may have been useful in some ancestor. So one of my favorite examples of this are the wisdom teeth. Some of you might have had your wisdom teeth out or are feeling some pains from them now. Wisdom teeth in humans are what we call vestigial, so they're no longer useful. And so they actually are reduced in form as well. They don't develop as much as our other teeth do. And we're going to see lots of examples of vestigial features in the next lesson as well. Next, we have Lamarck, and Lamarck is a really important scientist here. His theory, actually, we do hold some things from his theory true even still today, even though his theory was like in the 1800s, like I was saying before. So he was the first to suggest what I've called a mechanism for evolution. And what I mean by mechanism is a way that evolution could happen. And so his theory has two main principles. One is the theory of use and disuse. And what that means is the more I use a trait, the more highly developed it will become. And I'm going to use the giraffes down below as the example. He theorizes that as the giraffes continue to stretch their necks up and up and up, their neck also becomes more developed. It becomes stronger and therefore it becomes a larger neck. So that's like the first principle in his theory. The second part is that traits are heritable. And we know this because we've talked a lot about it in Unit 2. He notices that there is a connection between the parents and what the offspring have. So if one giraffe has a long neck, it also seems to have offspring that typically have long necks as well. So he notices that there is some type of heritability, there is some passing on of traits. Again, at this time, they don't know about DNA yet, so it's long before all of that stuff became apparent. But a couple of issues, as you can probably guess. This doesn't apply to every trait. So I use the example like if, for example, I work out my arms a lot and I get really big muscles, okay, I don't necessarily pass those muscles on to my offsprings. Okay. Likewise, let's say that I use my eyes a lot and I'm focusing my eyes a lot. My eyes are not necessarily going to get bigger and stronger. In fact, they might actually become weaker. So there's a couple of issues that happens with his theories. Now, the significance and why I was saying we still respect his theory is because he does, as I say, come up with the first kind of concept of how evolution happens, how we start to see a change in a population over time. So, a couple of almost like truths which are in his theory. One is that we know species do change over time. And how they're changing is based on their environment. So, thinking back to his giraffes example, if all the trees are really tall, well, then the giraffes with longer necks, they're going to be able to eat that food. So that actually benefits them in their particular environment. More about that will come up when we discuss Darwin, because that has to do more with the theory of natural selection. But as I said, as an early theory, this still holds a lot of truth to it. Also, we of course now know that yes, most traits are heritable, so they pass on from parents to offspring, and we see them pass on to future generations. So, really big important thing about Lamarck is that he really reopened the conversation on evolution, reopened the conversation on change in species over time, because as I mentioned, there was a lot of beliefs previously that evolution what was not even a thing. It was just that we were all placed here in the exact forms that we are today. So again, his sort of concept and his idea has opened the door for more scientists to start the discussion. So a couple of things I want to go over here, which most of you probably know about this, even from even geography and so forth, is fossils. So fossils are an extremely important record that we use to help support the theory of evolution. We're going to talk more about that in the next lesson. But starting off, just what is a fossil? So these are impressions or actual pieces of organisms that have become mineralized or preserved over time. So, what typically happens is that when something dies and they decompose, they'll leave behind oftentimes their hard tissue. Meanwhile, their soft tissue will decompose. And typically, this happens underwater just because that's a really convenient place for sediments to settle on. And so, that's usually where we're going to see that happen. And over long periods of time, lots of heat, lots of pressure, those will form into a mineralized fossil. So down here, what I'm meaning to show and what I'm the reason why I'm talking about this is that many people actually thought, oops, that fossils were just present day organisms that got trapped and they just died over time. But we now have evidence that that's not actually the case. So, first of all, we see fossils that don't exist anywhere in present day. So, they don't match perfectly any present day species. And as I said there are no fossils of most that are alive today because, as I mentioned before, it takes a lot of heat and pressure and a long period of time under sediments for those to form. Fossils are often very deep under the surface, and sometimes we also find them in really unusual or weird places. When we get to talking about Darwin, we're going to find out that part of his theory revolves around the fact that sometimes you find fossils in places like aquatic organisms are found on top of a mountaintop. So we know that over time, Earth has changed, and we're going to talk about that with Cuvier in just a few minutes. But what this tells us is that the Earth must be very, very old. Okay. Again, this is not necessarily popular with some religious teachings. So when people are saying these things, it's not necessarily a popular opinion. But if we're finding these fossils of organisms no longer around, that tells us the Earth must have been around for a really long time. So I want to tell you about a couple of different scientists. First one is George Cuvier, and he is a paleontologist. So his whole thing is studying fossils, essentially. So he notices a few things, and again, it's going to relate into our current theories of evolution later, which is that fossils of very simple organisms are found in all depths. So whether you're just under the surface or whether you're far under the surface. But the more complex organisms are only found at shallower depths. In other words, the younger rocks, the closer to the surface. And these are going to more closely resemble things that are around on Earth. So if you look at the little picture that I have inserted here, you can see that as you get shallower depths, closer to the surface, you have things that have more complexity. They might be similar to the ones below them, which are older than them, but they're not the same. They're growing more and more complex over time, usually. And then last but not least, as I said before, the rock layers contain fossils of many species that are not necessarily present before or after them. So looking again at the diagram, sometimes we see that there's actually nothing exactly like it in the layers above and below, okay? And so these support, again, a theory that life evolved from simple to more complex. So really deep fossils are really simple. As we move forward in time, they get more and more complex over time. Um, so going beyond Cuvier, so again, his whole job was a paleontologist. We have then his theory of catastrophism, excuse me. So he tries to basically explain why he sees those in the fossil record, those things I just mentioned. And his explanation is a theory called catastrophism. So basically, what he thinks is that some catastrophic event, natural disaster, climate change, and so forth, caused a mass extinction of organisms. And then those organisms were all replaced again with newer ones. So he doesn't think that they actually change generation to generation. He thinks that some natural disaster wiped them all out, fossilized them, and then in the following layer, you have a whole new set of organisms that are created. So his does not really explain why do they need to become more complex over time. Who's the person who starts to do that is Charles Lyell. Again, Lyell is a geologist, so he's studying rock formations. And his theory, which relates to evolution as well, is of uniformitarianism. And that's a fancy way for saying that geological processes happen really, really slowly, and they create fossils and they create changes over a really long period of time. So I was mentioning just before, this supports the idea that the Earth is extremely old. And so the organisms that lived long ago that are fossilized, they have changed over a very, very, very long time. And based on things like the rock cycle, which is essentially a geological process. So his theory or his principles involves that Earth has been changed by the same processes in past and present. So as I was saying, those geological processes such as plate tectonics, such as the rock cycle and so forth. The changes are very, very slow and gradual, not catastrophic. So as I said before, Cuvier is the theory of catastrophism. Big natural disaster events happen, they knock everything out, and then we start all over again. Lyell is in contrast to that. It's a very slow and gradual change that's happening. And natural laws that influence changes are constant and eternal. They operated in past as they did in the same intensity as today. So similar to number one, it's not that the plate tectonics got faster or anything like that. We're still using the same exact intensity. So, how this all comes together, and I was mentioning Darwin, until the mid 1800s, many scientists theorized on the evidence they saw around them, but no one had a tangible mechanism for evolution. How does evolution actually happen? Why these organisms get more and more complex over time. And so Lyell, who, as I said, is a geologist, one of his colleagues is the very famous Charles Darwin. And so Charles Darwin starts to take some of this fossil information, as I was mentioning earlier, and he starts to put together actually his theory on evolution, which is the theory of natural selection. So before we go into that lesson, which is coming up shortly. What I will ask that you do is to read, there's like a little textbook section here. It just gives you a bit of a context for what Darwin's mission was and what he was trying and aiming to do, which will help our conversation on how he actually comes back around to his theory of natural selection.